Welcome to the second lecture in week 5 of Machine Learning Foundations. In this week, as I've said before, we'll be focusing on Hermitian matrices. So we'll continue the discussion of Hermitian matrices. This class of matrices was defined in the previous lecture. And in this lecture, we will state and prove two important properties concerning the eigenvalues and eigenvectors of a Hermitian matrix.
Okay, welcome to yet another lecture of linear algebra module of machine learning foundations. Today we'll be looking at two important class of matrices, Hermitian and unitary matrices. So let's start with the first one. So what is a Hermitian matrix? So matrix A is Hermitian if its conjugate transposes itself. So let's look at a quick example what this means. Look at a matrix. Suppose A is this 2, 5, 3i and 3 plus 3i. So what is A star? A star is the conjugate transpose equals 2, 3 plus 3i, 3 minus 3i and 5. This is the conjugate, and then you have to take transpose, and that turns out to be just A. So this is an example of a conjugate transpose. You could do it in the other way also. First you could take transpose and then take the conjugate. The operations are interchangeable and you'll get the same result. And Hermitian matrices are a very important class of matrices because they constitute the set of orthogonally diagonalizable matrices. We'll look at that very soon. But let's understand Hermitian matrices a little more. You can observe that note. Diagonal entries of a Hermitian matrix are forced to be real valued. So you can't have complex values along the diagonal and then hope to get a Hermitian matrix. Now there are some important properties of Hermitian matrices which we'll look at. Let me state them as a theorem and prove them one by one. Okay, let's call this as properties. Properties of Hermitian matrices. The first important property is if a matrix A is Hermitian, then all eigenvalues of A are real valued, they can't be complex. Let's look at the same example to see what the eigenvalues are. Let's look at an example first. Before proving this, consider the example matrix A given above. For this matrix, if you calculate the eigenvalues, I would suggest you pause the video now, lecture video, and calculate the eigenvalues on your own. I'll just do this here. 2 minus lambda, 3 minus 3i, 3 plus 3i, 5 minus lambda. the determinant is actually turns out to be lambda square minus 7 lambda plus 10 minus square, which is the same as lambda square minus 7 lambda minus 8. This is the same as lambda minus 8 into lambda plus 1. So the eigen values of A are, say, lambda 1 equals 8 and lambda 2 equals minus 1. Now it didn't turn out by accident that these are real. I mean, in general, for any Hermitian matrix, it's always true that the eigenvalues are real. So we'll just prove this. Proof of 1. So let's start with the usual eigenequation. Suppose Ax equals lambda x. Obviously, just to emphasize, you can't x, which is the eigenvector, has to be non-trivial. We're looking at a non-zero eigenvalue. Now, to prove that lambda can only be real, it's enough to show that if I take the conjugate of lambda, I recover lambda. So lambda equals lambda bar. To do that, let's start by taking the conjugate of Ax star. This is the conjugate of lambda x. This, by the rules of conjugation, is lambda bar x star. Yeah. So here, conjugate of lambda. Yeah. Now, so this equivalently Ax star by rules of conjugation is x star A star equals lambda bar x star. This is what we have. Now let's multiply x on both sides. Lambda bar x star x. And now let's use the fact that A is Hermitian. So I get x star Ax equals lambda bar x star x. But this is a special x. Use Ax equals lambda x. So what do I get? I get x star lambda x equals lambda bar x star x. And this just means implies lambda times x star x equals lambda bar times x star x, and this finally equals equivalent to saying lambda equals lambda bar, since x star x is not 0, since x is an eigenvector or x not equal to 0. Yeah. So lambda is real. That's the end of this claim. Okay, I hope this is clear. Now we'll look at the second property. Property 2 of a Hermitian matrix, which says if A is Hermitian, then eigenvectors corresponding different eigenvalues are orthogonal. That is, Ax equals lambda 1x and Ay equals lambda 2y, lambda 1 not equal to lambda 2, then x dot y, which is x bar transpose y, is equal to 0. So that's the dot product in a complex vector space. As before, we could look at the example. So let's look at the example before. Recall what we had as A is 2, 3 minus 3i, 3 plus 3i, and 5 with eigenvalues which we calculated as 8, minus 1. Now, what are the eigenvectors? Again, let's find the eigenvectors. So, first thing is I want A minus the first eigenvalue, say A minus 8i times any vector x. So, this is 2 minus 6 is minus, 2 minus 8 is minus 6, 3 minus 3i, 3 plus 3i, and minus 3. This into, let's say, x1 into x2. We want this to be equal to 0. Yeah. And you can work out the solution on your own, leading to x equals 1, 1 plus I. So this is eigenvector 1. Okay. Let's look at the second eigenvector, A plus I into y. Let's call this y. So this would be 3 minus 3i, 3 plus 3i, and 6. This into, say, y1, y2 equals 0, 0. And this leading to y equals 1 minus I minus 1. It's a simple enough system, so I'm just guessing the eigenvectors. You could go about doing this in a more methodical way for larger matrices using Gaussian elimination. But given that this is a simple 2 cross 2 matrix, just by eyeballing you will be able to guess the eigenvectors. Now, if you look at x dot y, which is x bar transpose y, this is 1 comma x bar is 1 comma 1 minus I, and then you transpose it and take its dot product with this, and this is clearly 0. Okay, so in this example it's clear that so eigenvectors corresponding to 8 and minus 1 eigenvalues are orthogonal. And this is again not an accident, this holds true in general, just illustrated using an example here. So let's look at the proof of the second claim in the most general case. Okay. So again, so we have Ax equals lambda x, say lambda 1, and Ay equals lambda 2y, and we are given that lambda 1 not equal to lambda 2. And what do we have to show? To show x dot y equals 0. Yeah, and how do we show? Do this to x dot ay. This is x dot simply because ay equals lambda 2y, and this is equal to lambda 2 into x dot y. Okay. Second way of doing the same thing is x dot ay is x star ay. That's just the definition. X star is x bar transpose. But we also know that a equals a star. So I can write this as x star a star y, which is the same as ax star y. But ax is lambda 1 x star y. But lambda 1 comes out, so it will be lambda 1 bar times x dot y. Now this is equal to lambda 1 times x dot y. Now let me see, because here a equals a star, and here we used lambda 1 bar equals lambda from part 1 because it's a Hermitian matrix. So the net effect what we got is, let me call this equation 1, equation 2. So x dot ay equals lambda 2 times x dot y, and that is also equal to lambda 1 times x dot y. Okay, since lambda 1 not equal to lambda 2, yeah, we have, the only way I can get this equality is that I get x dot y equals x star y equals 0. Yeah, that's the end of the proof. Okay, that's the end of this proof. Please go over this carefully. And if I go back to this example, you can observe. Let me make a remark. The equivalent of Hermitian matrices in the real case is real symmetric matrices. So there's no question of conjugation, you just take the transpose. So trivially, I mean, that is to say that all real symmetric matrices are Hermitian. The second thing is, if no eigen value is repeated, that is have distinct eigenvalues, say n distinct eigenvalues for a n cross n matrix A, then A is diagonalizable. Why? Because now you use property 2 to obtain when linearly independent eigenvectors and use these eigenvectors to diagonalize the given matrix. Okay, there are two things that so the point is we just showed that if you know if eigenvalues are different, then the corresponding eigenvectors are orthogonal, and orthogonal vectors are linearly independent. And this is something I must have shown before. Okay, think about this. I'm not sure entire homework. Yeah. If x and y are orthogonal, show that x and y is a linearly independent set. It's a fairly straightforward thing to do. I mean, think about this. It's fairly straightforward. I can give you an oral hint. So if you want x and y a linear combination to be 0, you have to look at linear combinations of x and y that lead to 0. Say alpha 1 x1 plus alpha 2 y equals 0. And then, you know, take a dot product. Take a dot product with anything. Say x to infer the other coefficient is 0. Say alpha 2 equals 0, and do the reverse. That's a very strong hint. Please think about and solve this. So property 2 says that I mean if I have n distinct eigenvalues, from property 2 I can infer that I'll have n linearly independent eigenvectors, and I can stack these eigenvectors in a matrix and diagonalize it. That's really the claim that we are trying to make. Yeah. So in the example where A was 2, 3 minus 3i, 3 plus 3i and 5, yeah, we had two distinct eigenvalues, 8 comma minus 1, with corresponding eigenvectors 1 comma 1 plus I minus I comma minus 1. So A is diagonalizable. In particular, the way to diagonalize this is you can write A as first put a diagonal matrix with the eigenvalues So the idea of diagonalization is you stack, the idea is matrix with eigenvectors as columns, and this is a diagonal matrix with eigenvalues along the column, along the diagonal, and this is the inverse of the first matrix. Okay, so this is how you diagonalize it. Yeah. So that brings us to the end of Hermitian matrices. We'll revisit this in the context of diagonalization by proving that all Hermitian matrices are diagonalizable.
A quick summary before I wrap up this lecture. In this lecture, we discussed two important properties of a Hermitian matrix, which namely the first property states that all the eigenvalues of a Hermitian matrix are real, and the second property is if you have two different eigenvalues, distinct ones, then their corresponding eigenvectors are orthogonal. Now this led to a very easy conclusion that if I have n distinct eigenvalues for a n cross n Hermitian matrix or any matrix, then one can easily infer that it's diagonalizable because I get n orthogonal eigenvectors, and if vectors are orthogonal then they are also linearly independent. So I get enough vectors to diagonalize the matrix. So that's an easy case we can cover. But in general, Hermitian matrices need not have distinct eigenvalues. Even in that case, we will actually proceed to show in forthcoming lectures that they are diagonalizable, even if some eigenvalues get repeated. That's the claim that we are trying to get to finally.